Hello everybody, this is Vishnu Priya, your physics teacher. I welcome you all to Vidya Lakshmi School YouTube channel. Okay, so we are learning chapter 1 of grade 12 physics, electric charges and fields. Okay, so far we have learnt about properties of charges, Coulomb's law in scalar form, in vector form, and in terms of position vector, all those we have learnt. Okay, now in today's class what we are going to learn is principle of superposition and continuous distribution of charges. Okay, principle of superposition. When you have n number of charges, whatever the force is acting on the charge can be identified using this principle of superposition. Okay, the statement says when a number of charges are interacting, the total force on a given charge is the vector sum of the individual forces exerted on the given charge by all the charges. Okay, so it's very clear from the statement. So what will be the total force acting on the charge will be the addition of individual forces. Okay, for example, we consider charges. Okay, let Q1 be the first charge. Okay, Q2 be the second charge and Q3 be the third one, and you have n number of charges. I am representing Q1 as the nth charge. Okay, now what will be the force on Q1 due to Q2? Okay, it will be just, I am marking it as F12. Okay, I am considering all to be the positive charges, and F12 is going to be a repulsive force. Okay, F12 represents force on charge Q1 due to Q2. Okay, so its direction can be identified using the vector. Okay, using the R21 unit vector. R21 is the unit vector directed from Q2 to Q1. Similarly, we can mark the force on charge Q1 due to Q3. Okay, so it will be this way. Okay, F13 represents force on charge Q1 due to Q3. Okay, then R31 unit cap represents its direction. Similarly, force on Q1 due to Qn charge can be represented in this way. F1n represents force on charge Q1 due to Qn charge, and its direction can be identified from the unit vector Rn1 cap. Okay, now what will be the total force exerted on charge Q1? So for that you should add up all the individual forces. Okay, so F1 represents the force on charge Q1. It will be the summation of all the forces exerted on charge Q1 by the different charges. Okay, so F1 can be written as F12 vector plus F13 vector plus until F1n vector. Okay, so this will be the total amount of force exerted on charge Q1. Let's find out it in its formula. Okay, force between multiple charges, right? So F12 can be written as, F1, as a whole, what are the forces acting on charge Q1 can be written as, what we have seen, F12 plus F13 plus till F1n. Okay, this is the total amount of force exerted on charge Q1. Let's find out them in their formula. Okay, so F12, what do we know? We know from Coulomb's law, right? F12 will be equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R12 square, and R21 cap represents its direction. Okay, similarly F13 can be written as 1 by 4 pi epsilon naught Q1 Q3 by R13 square R31 unit cap. Okay, similarly for nth charge, okay, F1n, force on charge Q1 due to nth charge can be written as 1 by 4 pi epsilon naught Q1 Qn divided by R1n square Rn1 unit cap. Okay, so these are the individual forces, but we wanted the total force acting on the first charge, right? So for that what we have to do? We have to add the individual forces. So we get F1 to be equal to 1 by 4 pi epsilon naught q1 q2 by r12 square r21 unit cap plus q1 q3 by r13 square r31 unit cap plus q1 qn by r1n square rn1 unit cap. So this represents the force on charge q1 due to all other charges. Similarly, we can write force on charge 2. Okay, on charge 2 also, like all other charges will have its effect, right? So we can write it as F2 vector as 1 by 4 pi epsilon naught, okay, Q2 Q1 by R12 square R21 unit cap plus Q2 Q3 by R23 square and R32 unit cap plus Q2 Qn by R2n square Rn2 unit cap. Okay, like this we can write equations for n number of charges. Okay, so this is the force between multiple charges. Okay, in terms of their position vectors, can we write the distances in terms of their position vectors? Yes, it is possible. We have seen already how to mention them in terms of their position vectors or displacement vectors we say. Okay, so we will see how it can be written. Okay, so I am writing F1 itself. F1 vector can be written as F12 vector plus F13 vector plus till F1n vector, right? Okay, so F12, how do we write? In general, we write 1 by 4 pi epsilon naught Q1 Q2 by R12 square and R21 unit cap. This is in general. In terms of the position vectors, if we write, how do we write? 1 by 4 pi epsilon naught Q1 Q2 by R1 vector minus R2 vector the whole cube into R1 vector minus R2 vector. I hope you can understand how we have got this. We have done already about this in our previous video. If you are not able to understand, kindly go through the previous video. Okay, displacement vector we can represent like this. Okay, so this is F12. Similarly, F13 can be written as 1 by 4 pi epsilon naught Q1 Q3 divided by R1 vector minus R3 vector the whole cube. We are considering the magnitude alone in the denominator, and this represents the direction. Okay, so these are the individual forces in terms of their position vectors. Okay, as a whole, overall, what will be the total force? The total force can be written as F1, right? So F1 will be equal to 1 by 4 pi epsilon naught Q1 Q2 by R1 minus R2 the whole cube into R1 minus R2 plus Q1 Q3 by R1 minus R3 whole cube. Here you will have R1 vector minus R3 vector plus till until Qn. Okay, Q1 Qn divided by R1 minus Rn whole cube into R1 minus Rn. Okay, so this is how we represent the force between the multiple charges in terms of their position vectors. I hope you have understood how we have got the forces between multiple charges. Okay, the next topic that we are going to learn is continuous distribution of charges. Okay, so we know a property of a charge, like it is quantized. Okay, charge is a quantized one. Okay, so we cannot have with decimals. Okay, Q is equal to NE we have seen. Okay, N represents the number of charges, right? So if you have in a bigger area, bigger thing, we can neglect them and we will have it as a continuous charge distribution. Okay, as a whole in that particular surface or a line or the shape, charge is continuous, we will call. Okay, that is known as continuous distribution of charge. It can be in 1 dimension, 2 dimension, or 3 dimension. So with respect to that, we can say if it is 1 dimension, its charge distribution can be told as linear charge density. If it is 2 dimension, we can call them as surface charge density. And if it is 3 dimension, we will call it as volume charge density. Okay, we will see about them separately now. Okay, so linear charge density. Linear charge density is where we have a single dimension. Okay, you have charges, suppose a straight line you have, and charges are spread over here in this line. Okay, let the charge be represented as Q and the length be called as L. Okay, so then a linear charge density is usually represented by the symbol lambda. Okay, linear charge density is usually represented by the symbol lambda. Lambda is nothing but number of charges present in that line. Okay, so the amount of charge present in that particular line segment is known as linear charge density. Okay, so this is the equation to find out the linear charge density. What will be the SI unit of linear charge density? SI unit of linear charge density will be, SI unit of linear charge density will be coulomb per meter. Okay, what is the SI unit of charge? It is coulomb. SI unit of length is meter. So SI unit of linear charge density will be coulomb per meter. For example, if you have a ring-like structure, okay, if you have a ring-like structure, then what will be its surface charge, linear charge density will be Q by 2 pi r. Okay, 2 pi r represents the circumference of the ring, right? So then for a circular ring-like structure, you will have linear charge density as Q by 2 pi r. Okay, the next thing that we are going to learn is surface charge density. Okay, surface charge density. Okay, surface charge density is with respect to 2 dimension. Okay, it is with respect to 2 dimension. Okay, how do we represent a surface charge density? Is sigma is the symbol to represent the surface charge density. Okay, so sigma, we can have a surface here which has charges. Okay, so you have charges here, let it be represented as Q, and the surface area can be represented as A. Then surface charge density we represent as sigma. Okay, this is a Greek symbol which represents surface charge density. Okay, sigma, which is equal to the amount of charges present in the surface divided by the surface area. Okay, Q by A represents the surface charge density. Okay, then what is the SI unit of surface charge density? SI unit of surface charge density will be coulomb per meter square. Okay, SI unit of surface charge density will be, surface charge density is coulomb per meter square. Okay, if you have a sphere-like thing, then on its surface you have charges. Then what will be its surface charge density? We can represent it as sigma is equal to Q by 4 pi r square. Okay, 4 pi r square, where r represents the radius of the sphere. Okay, so its area is 4 pi r square, right? So surface charge density can be written as sigma is equal to Q by 4 pi r square. The next thing that we are going to learn is volume charge density. Okay, the next thing is volume charge density. Okay, you have a sphere, and around the sphere everywhere throughout its volume charge is being located. Throughout the volume of the sphere charge is being located, right? Then usually volume charge density is represented by a symbol rho. Okay, rho represents the volume charge density. So it is Q by V. Okay, where V represents the volume. Okay, so what will be the SI unit of volume charge density? It will be coulomb per meter cube. Okay, so SI unit of volume charge density is coulomb per meter cube. Okay, for example, you have a sphere, spherical bob like thing. What is the volume of a sphere? It is 4 by 3 pi r cube, we know, right? So rho can be written as Q by 4 by 3 pi r cube if r represents the radius of the sphere. Okay, so that's it for today's class. We will continue with the rest of the topics in our next class. Thank you all.